Hello everyone. Today I'm going to discuss about the topic IGBT, TRIAC and GTO. Before starting my presentation, let me introduce myself. I am Ayan Ghosh from Electrical Engineering Department from College of Engineering and Management, Kolaghat. My college roll number is EE2201. My university roll number is 107016220004. Now let's start today's presentation. At first we have index and under index we can see there are 3 points: IGBT, TRIAC and GTO, and under them each of them will cover the following bullets that includes introduction, construction, working principle and characteristics. Let's go to the next slide. Now at first we are gonna see about the introduction of IGBT. IGBT full form in electronics is an insulated gate bipolar transistor. It is a power transistor that combines an input MOS and an output bipolar transistor. IGBT is a three-terminal device. The three terminals are gate G, emitter E, and collector C. The next point is IGBT is a voltage control device. Again, IGBT stands for insulated gate bipolar transistor. It is a bipolar transistor with an insulated gate terminal. The IGBT combines in a single device a control input with a MOS structure and a bipolar power transistor that acts as an output switch. Let's go to the next point. The IGBT symbol shows that the IGBT symbol is similar to a power MOSFET but includes some important differences. The gate terminal G is insulated from the other terminals by a dielectric layer, unlike in a MOSFET as shown in figure. The two power terminals, collector C and emitter E, look like that of BJT. This IGBT transistor symbol clearly represents its characteristics as a combination of MOSFET and BJT. Now IGBT construction. The construction of an IGBT is made of four alternating layers of P-type and N-type semiconductors as shown in the figure. It consists of a P plus substrate and N drift region, a P body region and an N plus source region. A gate terminal is insulated above the P body region by a dielectric layer. This cross-sectional view reveals how the IGBT effectively combines the characteristics of MOSFET and BJT. Now the next point is the emitter and gate are metal electrodes. The emitter is directly attached to the N plus region while the gate is insulated using a silicon dioxide layer. The base P plus layer injects holes into N layer, which is why it is called injector layer. While the N layer is called the drift region, its thickness is proportional to voltage blocking capacity. The P layer above is known as the body of IGBT. Now the working principle of IGBT. When a positive voltage is applied between the gate to emitter terminals of an IGBT, it allows the flow of both majority and minority change carriers during its operation. Here are the simplified working steps. The application of a positive voltage between gate emitter terminals form an inversion layer near the surface channel region under the dielectric layer. The inversion layer provides low resistance paths for both holes and electrons to flow between emitter and collector terminals. The inverted P- region under the gate now allows electron flow from the emitter to the collector like in a MOSFET. Simultaneously, the built-in PNP transistor formed by P plus, N drift and P body regions inject holes into the N drift region. Movement of both holes and electrons reduces the resistance of the drift region, enhancing the current flow from the collector to emitter. Now, this combined majority and minority carrier conduction is the primary function of an IGBT that provides its unique advantage. Now, its characteristics. VI characteristics of IGBT exhibits some important graphs that give its switching behavior. Transfer characteristics. Plot of collector current I versus gate emitter voltage VGE as shown in figure. It indicates the control of output current. B, the input voltage. Output characteristics. Relationship between collector emitter voltage Vc and collector current Ic as in figure. Different operating regions like active saturation can be identified. Switching waveforms. Turn on and turn off transistor waveforms as shown in figure are useful to determine switching lines. Now what is TRIAC? A TRIAC is a semiconductor device with three terminals that allows and controls the flow of current, thus the name TRIAC. Instead of SCR, TRIAC is a bidirectional switch while SCR is unidirectional. It resembles two SCRs connected in a reverse parallel configuration with interconnected gates. Triggering conduction in both directions is achieved by applying a gate signal similar to how an SCR operates. Below is the symbol of TRIAC is shown. Now TRIAC construction. TRIAC is nothing but two SRCs are connected in inverse parallel with a common gate terminal. The gate terminal is connected to both the N and P regions due to which gate signal may be applied irrespective of polarity of the signal. Now let's get to the next slide. VI characteristics of TRIAC. The characteristics curves of TRIAC is basically works in four modes. Mode 1. In the first quadrant operation, VMT21 and VG1 both are positive. Mode 2. In the second quadrant operation, BMT21 is positive and VG1 is negative. Mode 3. In the third quadrant operation, BMT21 and VG1 both are negative. Mode 4. In the fourth quadrant operation, BMT21 is negative and VG1 is positive. So BMT21 represents the voltage of terminal MT2 with respect to terminal MT1 and VG1 represents gate voltage with respect to terminal MT1. Now, what is GTO? A GTO thyristor, which stands for gate turn off thyristor, is a three-terminal power semiconductor device that can be triggered in both on and off states using signals applied to its gate terminal. It was developed to address a key limitation of conventional thyristors, their inavailability to turn off using gate signals. Like thyristors, GTO thyristors are also bipolar. However, they overcome the limitation of thyristor by allowing turn off through the application of a negative voltage at the gate terminal. Now let's come to the next slide. GTO thyristor working. Turn on mechanism. When a small positive voltage is applied between the gate of cathode terminals, the P gate N cathode junction becomes forward biased. The injected holes triggered avalanche multiplication due to an impact ionization in the N cathode region. This leads to the generation of additional electron-hole pairs. Simultaneously, the injected holes from the gate also diffuse into the P-base region. This results in the accumulation of holes in the P-base region close to the gate cathode junction. As the current gain increases, more and more electrons are injected into the P-base from the N cathode due to increased base current. This further increases the hole concentration in the P-base. This positive feedback effect leads to a rapid rise in the currents and it keeps increasing exponentially. Once the combined current gain reaches unity, the device attains the state of saturation. In saturation state, all the three PN junctions, gate cathode, and anode base, are forward biased. This causes the device to fully turn on and it starts conducting in a forward direction. After turning on, no further supply of gate current is needed as the device maintains self-sustained conduction through the regenerative avalanche process until the anode current exceeds its holding value. Now its turn-off mechanism. When a negative gate pulse is applied, it causes the extraction of stored holes from the P-base region near the gate cathode junction. The removal of holes leads to the depletion of the P-base region below the gate terminal. This pinches off the flow of majority of charge carriers that were providing the main conduction channel. The negative gate pulse drives the rapid extraction of carriers from these filaments, dispersing the localized high current regions quickly to prevent thermal runaway. Once the sufficient holes are extracted, it leads to reverse biasing of the gate cathode J3 and anode base J2 junctions, distracting further injection. The remaining excess carriers in the N-base region recombine gradually over time to reduce the concentration of quasi-neutral levels. This recombination finally cuts off the anode current flow completely after the device is totally turned off. GTO thyristor characteristics. VI characteristics of GTO thyristor includes forward blocking mode, forward conduction mode, reverse blocking mode, reverse conduction mode, and turn off mode. Now for the reference, I took everything from the electrical machinery book by P.S. Bimra, and I also used my help from www.tutorialspoint.com. Now, thank you everyone.